So I guess this is also a good point to go over all these steps that we've covered in all these formulations. So the idea is that in these next couple of pages, we'll list out all the steps that are required for you to be able to solve a complete problem. Um, so once again, we'll start with the strong form. This is the strong form of the equation. We have a two-dimensional domain here. Let's say we are applying some heat flux through this edge. And the governing equation is this, where Q is uh, is the heat flux vector at a point. And if you take the divergence of a vector, you will get a scalar. So scalar plus a scalar should be 0. That's a scalar equation that we had. And this equation is nothing but an equation that is similar to the stress is some function of strain. So in this case, we are saying that heat flux is some function of the temperature gradient. Okay, and we have one essential boundary condition, which is this, and we have one natural boundary condition, which is all this. So if you take this strong form, you can write out the weak form and so on. In 2D elasticity, the similar equations that we had were div of sigma plus b is equal to 0, and the same equations. Now in this case, I want to point out that this is a tensor equation, but this one using a little abuse of notation, using the Voigt notation, you can write them as a stress vector related to a strain vector. Okay, so after you have the strong form and the boundary conditions, all you need to do is to do the method of weighted residuals and integration by parts. You will end up with this weak form for the heat equation. This is something that we derived, and you will end up with this weak form for the 2D elasticity problem. If you use the Voigt notation, then you can see that this strain tensor turns into the strain vector. This elasticity matrix, which is a fourth order tensor, turns into an array of two-dimensional matrix, and this strain tensor becomes a strain vector. So all we have done here is modified this term into this using the Voigt notation. And this is something that we will discretize and code up in the computer. So all this part is going on paper. We have not gotten to computer implementation yet. So the next step is if we want to solve this problem on an arbitrary domain. In this case, we have a nice rectangular domain, but we could in general have some arbitrarily shaped domain. So what we want to do is we want to solve this problem. We will discretize this entire domain into small, either triangles, rectangles, quadrilaterals, whatever. So you make small pieces of your domain, and you write each of these integrals as a sum over the element integrals. So this is an integral of some quantity over the domain, which can be written as sum of the element integrals. And the same thing for the natural boundary condition. You can break this natural boundary condition up into pieces of its elements, and not all the elements will have a natural boundary. So this sum will be over those elements which actually have a natural boundary. Okay, and then finally you plug in your finite element approximation. So in the case of heat conduction problem, we said that if you are using 3 noded triangles, you will have n times d, which is this. And here d, d1, d2, d3, they are all the nodal temperatures, right? So this is, for example, this element, you have temperature at this node, and this node. Those are the 3 degrees of freedom if you're doing this finite element approximation. So if you use this, you can come up with the temperature gradient, which is nothing but the derivative of theta with respect to x and derivative of theta with respect to y. So all you do is take the derivative of this matrix. The first row is with respect to x, that is 1. The second row is with respect to y, which is 2. And you get your temperature gradient. And at that point, you can plug that back into your weak form, and you will have your matrix equations. So this overall picture needs to be clear in your mind. Are there any questions or doubts about the steps of these overall big steps that we take in the formulation. The intricate details of all these, how to calculate all these integrals, we talked about in the last couple of lectures. For the special case when you have constant body force and constant heat source. So the same thing happens in 2D elasticity. We will set up our finite element approximation, but now this needs to be a vector approximation. So the first row is the same as this matrix, except that it will pick out the degree of freedom that is corresponding to the x direction. So this degree of freedom, dE1, this is corresponding to the x degree of freedom for the node 1. Similarly, but 3 and 5, they are the x degrees of freedom for nodes 1, 2, and 3. So what we are doing here is we are taking this row, multiplying it with this vector. That will lead you to the exact same kind of equation that you have here. 3 multiplied with 3 here. That is, so that's the approximation for displacement in the x direction, the same approximation in the y direction. And if you use this approximation, then you can find out the strains. This is all just pure algebra. So once you have this, you can plug it back into your weak form. And we saw that if you do that, you come up with these element stiffness matrices. So for heat conduction problem, the meaning of this B matrix, is different for these different problems. In the heat conduction problem, the B matrix looks like this. For the 2D elasticity problem, it looks something like this. Okay, but essentially we will always end up with this kind of a formula for the stiffness matrix. In the heat conduction case, it is going to be 3 cross 3, and in the elasticity case, it is going to be a 6 cross 6 because there's 2 degrees of freedom per node. So finally you assemble them, and after you assemble them, you will get a global system of equations. So this is the the most important equation that you should end up with. So finally, after you make all these approximations, plug it in, you will end up and assemble the equations, you will end up with this equation. And we know how to solve this equation. You have to enforce boundary conditions. You say that there are some degrees of freedom that are specified, which are these. So if you know ds, you can calculate df. Those are the free degrees of freedom. Okay, so this is something that we did even for the one-dimensional problem. Once you calculate your free degrees of freedom, you can go back and calculate the reactions for your structural problem. And once you have this solution, you can also do some post-computation. And post-computation in 2 dimensions means that you are going to plot the temperature value at all the nodes. So what does that mean? You are going to plot the value of the temperature at each of these nodes. And typically, we also generate a color plot, and the MATLAB command that you will find is helpful in this case is called patch. So the idea is that you go to each element, you plot the value of the temperature at each of its nodes using this patch command, and you can there is an option in this patch command to use interpolated color. So what it will do is it will generate a color plot of this entire domain for the temperature problem, where you can see how the temperature is varying across your domain. Okay, and similarly for the elasticity problem, we also plot the displaced shape, and this is also something that you must have seen in the truss problem. You had the dotted line for your original shape, and you can plot with a solid line the displaced shape. And so to do that, you would have to first calculate what are the new positions of each of these nodes. So let's say you find out all these D. and you have the original coordinates x of the mesh. So how would you calculate what is the displaced shape? This d is just the displacement, right? So to calculate the displacement, you would have to, of each node, you would have to, let's say, node I. It would correspond to degrees of freedom 2i minus 1, comma 2i, right? And then you would pick out those degrees of freedom from this global displacement vector, add it to your original coordinates. So if you remember from the truss problem, I had a command in there that said x nu is equal to x plus displacement, or magnification times displacement. Did anybody take a look at that? How the truss was plotted? No? Okay, so take a look at that, because that's what you are going to use to plot this. And normally, if the displacements are very small, we also magnify our displacements to make it look different from the original configuration. And another important point here is that the stress distribution over all the elements. So what do you think is going to happen if I apply an end load here and I calculate the displacements using this finite element method? How do I plot the stresses? What should the stresses look like? So basically what I'm asking is, let's say go to one triangle. What would be the stress profile within that triangle? So it will be constant, because we have assumed that our displacement is going to be linear. For the three-noded triangle, the displacement is going to be linear within an element. So all the stresses, which are derivatives of displacement, which are proportional to the derivative of displacement, they are going to be constant. So the idea is that you would have to plot this triangle with one color, this triangle with another color, and so on. And if you look at the edge of the triangle between edge between two triangles, you will see that on one side the stress value is something else, and on the other side the stress value is something else. So on this edge, it would seem that equilibrium is not satisfied. But again, the idea is that the equilibrium will be satisfied weakly over the entire domain. So even though what the stresses that you have calculated from your finite element problem will not match at the boundary, even then this is just an artifact of your of the assumption that displacement is going to vary linearly in an element. So what we do sometimes is, for example, here, let's say you have this node, which is and the elements that are connected to this node 1, 2, 3, 4. Let's say each of the element has a different stress inside the element. So what we would normally do is calculate the average of all these stresses. And these are, again, post-computation procedures. When we talk about quadratic elements and higher order elements, I'll tell you there are some other ways of getting an average value of stress at each node. So if you go to this node, there are these two triangles, there may be other triangles. You have to average all those values and put them here. And that is again something that you will plot with the patch command. Okay. So yeah, another reason that we call this triangle is also called the CST element, which stands for either constant strain or constant stress triangle. The three-noded triangle is called the CST element. So this is the outline of all this procedure, and your MATLAB code actually starts at this stage, right here. When you want to calculate element stiffness matrices, that's where your MATLAB code starts. You don't have to code up all the formulation or anything. So in your finite element code, you first read your input file. You will have a bunch of coordinates, just like your one-dimensional problem. You have all the bunch of coordinates. You get all those coordinates, calculate all the element stiffness matrices, assemble them, and solve your unknown displacements, and then plot the output. That's basically the outline of your finite element program for 2 dimension. Okay, so let's take a look at another type of element that we have in 2 dimensions. We have what is called a 4-noded quadrilateral. This is denoted with Q4. So in general, we can also have quadrilaterals which are arbitrarily shaped. They need not be nice rectangles. But for now, let's just consider, this regular rectangles which are oriented with x and y dimensions. So the idea is that you have the same domain. Instead of discretizing it with triangles, you are just dividing it up into rectangles. And let's try to find out what are the shape functions for all these rectangles. So does anybody remember how did we find out the shape functions for the triangles? Let's say I have a domain. I go to a particular element. How do I find out the shape functions for that triangle? Right. Right. So we said that for the triangular case, we needed to find the shape functions by pretty much. Let's take a look at this. So if somebody gives you the element coordinates, you can set up these equations, and you can calculate your shape functions like this. But in this Q4 element case, and especially in the case when we have a nice rectangle that is oriented along x and y, the easy way to construct all these shape functions is by actually multiplying the one-dimensional shape function in x direction. So this, if you remember, was the one-dimensional shape function in the x direction. This is n1 and this is n2. And similarly, in the y direction, you have this one-dimensional shape function. This is n1, which is 1 at node 1, and this is n2, which is 1 at node 2. So if you multiply these shape functions together, you will be able to construct a shape function, set of shape functions for this rectangular element. Okay, so let's take a look at this node 1. If you go to node 1 and pick this n1x, right? This is a shape function that varies from node 1 to node 2. It has value 1 here and goes to 0 here. And similarly, consider this shape function 1 for the y direction. It has value 1 here and goes to 0 here. So if you multiply those two, you get a shape function for this node 1. So let's check whether this shape function actually satisfies our intuition about the finite element. If I plug in the value of x as 2, 3, or 4. So if I plug in the value of x as 2, what happens? So this n1 term will go to 0, right? So at both nodes 2 and 3, this n1 term goes to 0. At node 4, if I plug in the value of y here, then this n1y goes to 0. So at all these 3 nodes, 2, 3, and 4, the value of this shape function goes to 0. Okay? And only at node 1, if I plug in x is equal to 1, x is equal to x1, and y is equal to y1, then you can see that this would be 1 times 1, which is 1, right? So this is how you would construct shape functions for quadrilaterals and for the specific case of rectangles. And later on, we'll see how we can actually generalize this procedure to map this quadrilateral or rectangle to a general quadrilateral. So what would be the shape function for 2? n2x and 1y. And n3 would be So another point here is that we usually take all these nodes in a counterclockwise direction. We say that our node is going to start at 1. You can pick any one, but we want to. This is a convention. This is not going to affect your calculations much. But if you choose node 1 here, we go in a counterclockwise direction and number all the nodes that way. Okay. So node 2 is here. Node 3 would be n2x times n2y, and node 4 would be n1x times n2y. And you can verify that each of these shape functions, they have the value 1 at their node and value 0 at every other node. Okay. So the definitions of all these one-dimensional shape functions are also right here. These are the same definitions that we used for our one-dimensional problem. These are Lagrange shape functions between 2 nodes. The same way that we set up Lagrange shape functions for 3 nodes, this is the similar formula that we have for 2 nodes. Okay. So what do these shape functions look like? So let's consider n1 first. So this is node 1, this is node 2, this is node 3, and this is node 4. And you can see that if you were to plot this shape functions for each of the 4 nodes, what they would look like is this quadratic curve. On this edge, you can see that this function has a, if you take that plane, that value of that function is a straight line, which is expected because this was the shape function for this edge. Similarly, on this edge, the shape function was supposed to be linear. So on these 2 edges, the shape function is linear. But within the domain, the shape function is not linear. Why? Because both of these shape functions are linear. There will be a quadratic term which will come in corresponding to x times y. Okay, so these kinds of shape functions are called bilinear shape functions. So the idea is that all these 4 points, they obviously do not belong to the same plane, right? So you cannot pass a linear a plane through all these 4 points. So there is a little bit of a curve to each of these shape functions. This is n1, n2, n3, and n4. All right. So let's, if you remember from the three-noded triangle case, does anybody remember what is the value of this for the triangle case? What is this? Sum of the shape functions at any general point within the triangle. So that is, as we saw, it was, we can prove that the sum of the shape functions within the triangle is 1. And what is that? Does anybody remember what we called that property? Completeness. So the same type of thing happens here. You have this rectangular element, go to a point, any point within this element x, y. And let's try to sum this thing up. And if you do that, let's see what happens. You can collect terms for n1x, that would be this and this. What you would have in the bracket would be n1 plus n2 times y, right? And similarly, if you collect terms for n2x, you would have n1 plus n2y. So what is the value of this? What is the value of this term? For any value of y, if you go for any value of y, if you go somewhere in this element, the value of n1 plus n2 is just a constant line 1, right? So that's what's happening here. So this is 1, this is 1, which leads to that n1 tilde x plus n2 tilde x. and this itself is also 1. So we end up with the same property that sum of the shape functions at any point for alpha is equal to 1 to 4 is equal to 1. And this is a property that's common to all finite elements. You can enrich your shape functions. You can add more shape functions on top of this, but as long as there is a basis in the finite element shape functions that you've chosen that satisfies this property, then your finite element basis is called complete, and that helps you in convergence. If your basis is complete, then as you refine your finite element mesh, you can expect that your solution will approach the exact solution. Okay. So I've already mentioned this. You remember this is the way that we were calculating the triangular shape functions. If you have if you have a triangular shape functions, you can express them as a linear polynomial in x and y. And in this case, there is one extra in the case of the quadrilaterals, there is one extra term that comes in because of multiplying one-dimensional shape functions in x and y. So another way of looking at that is using this kind of a diagram. If you have higher order elements, this we will see again later on. But if you have higher order elements, you can list the powers of x along the x-axis. You can list the powers of y along the y-axis, and you can see that the triangle captures these coefficients, and this 4-noded rectangular element captures all these 4 types of polynomials. So as we increase the number of degrees of as we increase the degree of the polynomial in the x and the y, we will be including more and more terms in our approximation. So we would expect better and better accuracy of our finite element problem. Okay, so after that, what do we do? Once we have built up our approximation, now that we have n1, n2, n3, n4, we just calculated them by multiplying those two x and y together. All that we need to do is to write out our approximation for the solution in one element. So again, for the heat conduction problem, we are trying to find the temperature at different points in the element. So what we need to do is to use this approximation, which takes the exact same form as before. We have 4 shape functions, 4 degrees of freedom, each at one node. And again, there is no direction to it because this is a scalar problem. This is a temperature. So these are all the 4 temperatures at the 4 nodes. You multiply them with the shape functions, and you will get the approximate value of the temperature at any point. And using this, you can also calculate the temperature gradient, in which this B matrix turns out to be that there is one extra column in this N matrix and this B matrix. So as you can imagine, you can build 5-noded polygon, and that would have 5 columns in this case. And the similar thing happens in 2D elasticity case. Your degrees of freedom in this case would be labeled for the 4 nodes. You will have 2 degrees of freedom at each node. And once again, you have this extra term in your shape function matrix, and your degrees of freedom will now become 8. There are 8 degrees of freedom for this element, and if you multiply this matrix by this vector, you will get a 2 cross 1. If you multiply this matrix with this vector, you will get a 2 cross 1, which would represent the displacement in the x direction at that point and displacement in the y direction at that point. Okay. And similarly, in the B matrix, you will have this one extra set of components in your B matrix. The same D vector that comes in here. So this is the finite element approximation. You plug that into your weak form, and you will end up with the same sort of element stiffness matrices. So for heat conduction, if you remember, it was B transpose conductivity matrix B. Now we have just switched the definition of this B. So this B, instead of being a 2 cross 3, it is now a 2 cross 4. Okay. So what would be the, I've already written here, the dimensions of the K stiffness matrix are 4 cross 4. What is the dimension of B transpose? For this 4-noded element? So B transpose is this transpose. That would be 4 cross 2, right? So B transpose is 4 cross 2. K is 2 cross 2, and B again is 2 cross 4. So the result of this matrix right here becomes a 4 cross 4. But the difference from the triangular case is that this is not constant. Okay. Since this is not constant, you cannot pull it out of your integral. You would have to do, in general, all these integrals numerically. So similarly, you have all your element stiffness matrix, element force vector. You will get these two quantities, and here I'm denoting this integral to be over the element domain. So this is supposed to denote the element domain for that quadrilateral. This empty square is supposed to denote only the boundary of that square. Okay, so this is a boundary term. This is the domain term. They both lead to the F vector. And the same thing happens in 2D elasticity, where you get a 8 cross 8. And the reason you get an 8 cross 8 is that B transpose, this B transpose is 3 cross 8. Sorry, the B transpose is actually 8 cross 3. D matrix, some of you actually asked me even last time, this D matrix is the elasticity matrix that we had introduced in the very first lecture here. So for example, if you have a plane strain or a plane stress problem, this thing is your D matrix for a plane stress problem, and this is a D matrix for the plane strain problem. All that you need to do here is to evaluate these integrals over the domain of these rectangles, and these integrals are only for rectangles. They can be expressed as dx dy. Okay. Later on we'll see how to map this rectangle to a quadrilateral and what happens to this dx dy then. So once you do that, all you have to do is to assemble these things and solve the same equation, enforce a boundary condition, and you have the same type of result. So you should be familiar with this procedure. You start with your strong form, get the weak form, discretize it, find out your element stiffness matrices, assemble them, enforce your boundary condition, and solve for your unknowns. So either whether you're using a triangular element or a quadrilateral element, it doesn't matter. The steps of the formulation, they are going to be the same. Okay. So let's take a look at one of the examples that is also in your book. So this is the example where we are solving this Poisson equation. So this Poisson equation is very similar to the heat conduction problem. Here U is supposed to be a scalar value, and this operator grad square is nothing but, if you go back to the lecture notes, and if you take this equation, you take this q, substitute minus kappa times grad of theta into this value here, you will get minus kappa square, this grad square of theta, and you can assume that kappa is an identity tensor. You would get this equation back. So this is the same equation that we are solving in this example. This Poisson equation is the exact same problem that we are solving in this case. So we are given that we want to solve this equation on this type of a square domain where the boundary conditions, so this domain varies from minus a to plus a, it's a square domain, and we shall consider the following boundary conditions, that u is equal to 0 on the entire boundary. So what we are essentially saying is that the value of the temperature, if you want to think of this u as temperature, is 0 on the entire boundary. And so we have to solve this equation for this entire domain. And this is also true for problems in structural engineering. We do not need to solve this entire square problem because there are some symmetries associated with this problem. We are being given that since u is 0 on all the domain boundary, f naught is constant. Therefore, the entire problem has a biaxial symmetry. If you take this x-axis, the value of u at this line will be same on both sides of this square. So you can reduce your problem in all finite element problems. If you have symmetry, you can reduce your problem size to by either half or 1/4 or 1/8. So can anybody tell me how many times can we reduce our finite element problem in this case? So if we consider only 1/4 of the problem and we replace the boundary condition at this edge and this edge by a symmetry boundary condition, this is also something that you might have done in structural analysis. If you have a symmetric structure, symmetric loads, symmetric constraints, you can actually solve half the structure, right? So this is something that after considering two symmetries, you can consider only this small 1/4 domain. But in addition, you can also divide this entire domain into 8 parts. So if you look at this line, this diagonal, and this diagonal, the problem is symmetric with respect to those two axes also. So not only the horizontal and the vertical, but the problem is symmetric with respect to these two diagonals also, which means that you can go ahead and consider only 1/8 of the entire domain. So if your original problem had 1 million degrees of freedom, you have just cut down your problem size by 8 times. Okay, so you have to, in a large problem size, you must try to find if the problem is symmetric and try to find what is the shortest or the smallest problem that you can solve and still get the correct answer. So in this case, it turns out that if we just consider, so this was the entire domain, if we just consider 1/8 of the domain and modify our boundary conditions a little bit, we can get away by solving just 1/8 of that domain. And let's take a look at what these boundary conditions would be. So on this bottom edge, we want to say that the displacement, it should be whatever value we get from this side of the solution should be equal to this side of the solution. So what we are saying is that our solution, does not vary across this edge. And another way of saying that is that du dn, where n is the normal vector to that edge, du dn is equal to 0. Okay. Um, so essentially what we have done is we have discretized this 1/8 of the problem, and I'm not sure if this is visible on your handout. So we are taking this 1/8 of the problem and we have divided it up into 4 triangles. Can you see that on the handout? So you can barely see that there are 4 triangles, and it so happens that for each of those 4 triangles, the stiffness matrix is this. For all of those 4 triangles, this is the stiffness matrix. And for all of those 4 triangles, this is the force vector. And you can verify the force vector by the following. What is the area of each of these triangles? So let's consider this small one triangle. What would be the area of that triangle? So A, we are assuming, is 1, and that is the width of this triangle. So A is 1, height is 1. So in this equation right here, A and B both are equal to 1. So the area of the triangle is half. Okay, and if you take the area of the triangle, multiply it with the F0, that is the constant heat applied to it, then we saw that the force vector was going to be F0 delta over 3 for each of the 3 nodes. That's exactly here. So this is F0 delta over 3 for each of the 3 nodes of the triangle. And at that stage, there is another mesh which is a finer mesh, but let's just talk about this one first. So there is some algebra that you can take a look by yourself. After that, all that you need to do is to assemble the global stiffness matrix. So you can see that there are 6 degrees of freedom in this case. Those 6 degrees of freedom are 1, 2, 3, 1, 2, 3, 4, 5, 6. So these are the 6 degrees of freedom at the 6 nodes of the mesh. And if you assemble your 3×3 stiffness matrix for the entire domain, this is what you will get. And after that, we know how to solve that, because in this case, the essential boundary condition is that nodes 4, 5, and 6, have to have the value u is equal to 0. So if that's what we need to solve, then these 3 equations, these last 3 equations, these values are known to be 0. All that we need to do is to use our boundary conditions that we talked about earlier and solve the first 3 equations. Okay, so maybe what we'll do is I'll let you go over this example by yourself in the books. How many of you don't have this book by Reddy? So this is example from the book by Reddy. Okay, so what I'll do is I'll post this example along with the lecture notes. You can take a look at it, and if there's any quantities in there that you don't understand how they got these values, then you can again ask me about that. All right, so let's stop here, and I'll see you on Friday.